do we have clouds or other things in the air tending to block sunlight? Again, remember, troposphere is largely warmed by sunlight getting all the way through and then actually getting absorbed by the ground rather than being reflected. So having the sun high up and having a low albedo will help there. But if we've got clouds in the way, or smoke or other things, not as much sunlight comes through. Our ground's warmed up less going to the air. Of course, nighttime, there's no sunshine coming down anyway, and clouds provide a bit of a blanket effect. So nighttime clouds to make it warmer, daytime clouds cooler. Okay, what's the balance? That's one of the tricky things, making it hard to predict exactly what will happen with different factors impacting the climate. But during the daytime, clouds make it cooler out there. For example, certainly if you go out and those clouds above me look really black, okay, I think I'll go back inside. But if they look very black to us, that means they're doing a good job of blocking the sunshine. For a satellite up above, those clouds will look very white because almost all of the light from the sun is bouncing back up into space, very little of it's coming down to us below. Volcanoes. Ash, that'll block the sunshine. So volcanoes can cool things off. In fact, a very big volcanic eruption can noticeably cool the Earth down for a year or even a few years. Some of the biggest ones recorded in history. Or if we go back in geologic time, things bigger than any in recorded history, some of those may have cooled things off for many years. Besides the ash up in the air being an issue, you've got various gases. On the one hand, volcanoes do put out noticeable amounts of carbon dioxide, so that could warm things up. But other gases, for example, sulfur oxides, and different volcanoes produce different amounts of these different ones. But the sulfur oxides, those are good for making clouds and acid rain. So a volcano that puts out a lot of sulfur oxides, water sticks to that well, makes cloud droplets, and we'll see less light getting through and cooler conditions as a result. Yeah, eventually the stuff settles out with the atmosphere and things go back to normal, but volcanoes can cause a noticeable cooling for a period of time. Plates moving around, lots of effects. For example, if we don't have any land near the poles, then there's not much we can do to build glaciers. And snow has to pile up on land in order to build a glacier. So we'd like to see relatively warm conditions. Or again, depending on where continents and oceans are and how they're connected, we might see currents that either favor bringing warmer water to the poles and thus keeping it from getting very cold, or ones that tend to block these warmer winds and currents reaching the poles and allow it to get very cold at the poles. Depends on our continent arrangement. Continent-continent collision builds our great big mountains like the Himalayas. That's a lot of rock exposed to air. And various types of rocks can react with air, use up the carbon dioxide and turn it into minerals. And that'll tend to make things cooler. Or do we have conditions where there's lots of living things that are using up carbon dioxide from the air? Many possibilities there. And there's our carbon dioxide wiggling around. It's got some energy that's absorbed. Lots of things affect the climate. Sunshine's our main source of energy in the atmosphere. Well, what's the sun doing? It does go through various changes over time. And then how much gets back out of space. Both of these vary. In the very long term, over geologic time, the sun is getting brighter and warmer. Now, it's a very slow process, but this does mean that maybe in a few 100 million years, Earth is going to get too hot to be good for life. Not something you really need to stay up at night worrying about, but illustrates this long-term trend. But there are also plenty of shorter term ups and downs in what the sun's doing. One of the best known cycles, because it's relatively short, easy to watch it happen, is an 11-year cycle of relatively higher and lower levels of activity. A fairly easy way to check this is to monitor the number of sunspots observed. We now know that sunspots are basically big storms on the sun, and you get more of them when the sun is more active, putting out more energy. Fewer of them and the sun is calmer. And so you can see the ups and downs of this chart of sunspot records. These relatively regular occurring spikes, those are your usual 11-year cycles up and down there. But you notice they're not the same all the way across. You've got a few extra high ones and some periods of very low where there's not many sunspots at all. The Maunder minimum, Dalton minimum, named for observers who notice this pattern in the sunspots. Those are intervals when the sun was extra calm, a little less energy, and things were somewhat cooler for the climate for those years. Right now, we're in an interval of low activity. Sun's having many fewer sunspots than usual for all the way through its cycle the past couple times. So that tends to push things cooler. Now, of course, there are other things going on. How do they all add up will give us our total result. Milankovitch cycles. These are very long-term wobbles in the Earth's orbit. For example, over time, we go from having the Earth going basically like this around the sun. Gradually it turns to being like this around the sun. So that will change between whether the northern hemisphere or the southern hemisphere is having its summer in July, or basically will slowly move through the year. What part of the world is getting summer and winter when? Similarly, there is slow variation back and forth by about a degree or so in just how much the Earth is tilted compared to the sun. And the Earth's orbit gets a little bit more circular, a little bit more oval, not nearly as much as I'm doing with my fingers, but you actually have to see something, so I'm exaggerating there. All of these will have effects on just what part of the globe is getting how much energy from the sun at what time of year. Doesn't sound like all that big a difference, but remember, that's what's driving our seasons. What part of the globe is getting more or less energy from the sun at what particular time? So, for example, when we look back into the most recent ice ages, the effect of the Milankovitch cycles matches quite nicely with when do we see glaciers advancing, burying practically all of Canada and a good chunk of the northern U.S., versus glaciers melting back to just being in Greenland like we see today. Just a few degrees difference in average global temperature is enough to make that change when you're close to the tipping point. So lots of things affect the temperature, not just carbon dioxide, but we have what the sun's doing, other greenhouse gases. For example, one group of very strong greenhouse gases are chlorinated fluorocarbons, which kind of obviously are chemicals that contain chlorine, fluorine, and carbon. But what else about them? Why would you mention them? Well, it turns out chlorofluorocarbons, for one, work very nicely to work your refrigerator. They go through changes between liquid and gas, similar to what water does, quite readily at temperatures useful for refrigeration. They also work quite nicely to be the stuff that you put in your aerosol spray can to help make it spray. But when those gases then get out into the air, whether your refrigerator gets leaked or you've sprayed the spray, whatever like that. They'll mix around with the air, and some of them make it up into the stratosphere. Once they're there, chlorofluorocarbons react very easily, partly by breaking down and creating more reactive chemicals, with the ozone layer. And so putting these into the atmosphere tends to lead to less ozone in the stratosphere, what's commonly known as the ozone hole. In turn, the ozone absorbing UV light coming in. If the UV light is absorbed up there by the ozone stratosphere, it's not absorbed by your DNA in your skin to cause mutations and give you skin cancer and sunburn and other bad things. And not just us, but plants, animals, those are going to be affected by having too much UV as well. So there was an international agreement. These are causing problems, and so trying to largely eliminate the use of them. And with eliminating them, one, the ozone is doing better. We are seeing some recovery from the hole. And two, we aren't seeing things being quite as hot as they would have been if we were still using these chemicals as much as we had been. Now, there are complications. For example, yes, manufacturers largely banned. However, there are a number of major factories in China still producing them illegally, but they're making money because they're companies that like the way they're useful for different functions, and so they're buying them even though it is illegal. And of course, the various leaks from that continue to lead to the problems there. There are a number of longer-term climate cycles on the Earth. For example, the El Nino effect. Probably the most well-known in terms of the name having reached the general public. There are several others, similar sort of thing, but that's the one where the name has spread a lot. The name comes from the fact, means the child or baby, male, in Spanish, and refers to the fact that this weather phenomenon tends to be conspicuously notable by changed conditions along the coast of South America, the west coast, starting around Christmas. So the baby in question is the Christ child that it's named after. And this shift in the local weather and climate conditions leads to a number of connected factors that produce around the world weather that's different from your average. So, as we burn things, we don't just make carbon dioxide, we also make little specks of largely black stuff in the smoke, and this spreads around. In the air, that'll tend to block some of the sunlight. Settling out of the air, what it lands on gets darker, especially if it was white, like say snow. So as we improve our pollution control, we're getting somewhat less soot, and snow being whiter will tend to reflect more, help cool things off. Of course, clouds tend to make it cooler, less soot, less of those clouds. What's the balance? A little challenging there. We know that while it's in Earth's orbit, there are different variations possible in currents, many things. And these different factors can affect each other, and we may see either positive or negative feedback. Positive feedback refers to a case where something happening leads to it happening more. Classic example of that is the effect of having ice or snow on the albedo. If we've got lots of snow and ice, it's typically pretty white, so it's reflecting lots of light and making it cooler. If it's cooler, then we'll tend to see more snow and ice happening. More of the Earth is covered in that, reflects more, gets cooler, and we've got a sequence. Tends to make it happen more. Or if we get going the other way, more ice melts, Most of the things are darker, lower albedo, so they absorb more light, get warmer, warmer, more melts. And we tend to keep going that way. Yeah, eventually something else will kick in, but that particular part. Another one, probably all too familiar, that feedback screech of a microphone. Well, what's going on there? The problem is that microphone is not just picking up what it should, but it's also picking up that screech coming out of the speaker and making it louder, which makes the microphone pick it up more and send it through the speakers and make it louder. And of course, it's a negative experience hearing that, but it's an example of positive feedback. More noise going into the microphone tends to make the microphone make more noise come out the speakers. So we've got many, many factors. These will all add up, kind of like wave interference. And so, yeah, temperature year to year, we've got variations up, down, even day to day. And pretty squiggly. Judging that this one is averaging out steady, this one, the average is creeping up a little bit. Not easy to see by looking at that squiggle. I mean, our highest temperature for both in this time interval was actually back here in the beginning, but our averages are getting higher. So to really be able to tell, are we seeing something like this going on? What we need is good records, especially over long term. Now we can go back and try to look for things that may be preserved naturally that provide some clues about the temperature patterns, and there are quite a number of different things that we can look at that give us some information about temperatures in the past. But of course, that's not going to be as precise as if we actually had somebody with a thermometer that long ago. What do we see when we look at these long-term patterns? We see that things are, on average, getting warmer. Now again, this is a global average. This does not mean that every single spot on the globe is getting warmer. Some places could actually get colder, but more are getting warmer than are getting colder. And yes, there are ups and downs, but it's the long-term global average. We are seeing warming and other changes associated with that. So, for example, in precipitation, the amounts of rain and snow, and hail and sleet, we're tending to see changes. Some places are getting wetter, some are getting drier. Also, we tend to see a shift towards fewer bigger storms, more of the rain kind of all at once, less generally spread out. More rain all at once, that's more what you want to have to make floods, not so great for plants growing nicely, a good balance. When we look at ice, we're seeing increasing melting in general. This diagram here shows the amount of sea ice in the Arctic over time and over the past several decades. Yes, there are zigzags up and down, but overall it is decreasing. Glaciers, well, there's some variation because some places are so cold that warming will still be below freezing. Warmer air, whether it's below or above freezing, goes along with more evaporation. So we can have more water vapor if the temperature, though below freezing, is not as below. Say -1 Celsius, we can have more moisture in the air than if it were -40. And so if we have a glacier in an area that stays below freezing all the time and doesn't get very much snow, if things get warmer but still below freezing, we might get more snow, and that glacier could actually grow. But once we get above freezing, we'll see more melting. Different glaciers in different places will show different patterns. So a glacier growing, no, that's not proof that things are getting colder. What are glaciers around the world doing? Look at that.